Imagine navigating 1,000 miles blindfolded, relying only on your footsteps and a stopwatch to hit a target the size of a window. In the modern theater of war, satellite navigation is no longer a guarantee, it is a vulnerability. The sky over Eastern Europe has become a graveyard for GPS signals, forcing a return to pure physics. For decades, GPS was the ultimate guiding light. But today, massive electronic warfare systems like Russia's Krasuka-4 saturate the skies with white noise, drowning out the fragile whispers of satellites orbiting 20,000 kilometers above. When those signals die, digital maps freeze, and smart weapons turn into blind metal. It is not just jamming, it is spoofing. Advanced transmitters broadcast fake GPS coordinates, tricks that convince a drone it is flying safely off course when it is actually heading straight into a hillside. In this electronic fog, relying on external signals is a fatal mistake. Designers had to look inward. This is the reality of modern peer-to-peer conflict. The electromagnetic spectrum is a chaotic battleground where the side that depends on the cloud loses. To survive, weapons must become entirely self-contained, autonomous mines that need no satellites, no radio links, and no external help to find their targets. How do you guide a drone across hundreds of miles of hostile territory when the sky is completely silent? The answer lies in a technology developed during the height of the Cold War, stripped of its heavy mechanical gears and shrunk down onto a piece of silicon smaller than a single grain of rice. Welcome back to Weapon Science. I'm Ethan Walker. Today, we are breaking down the incredible engineering of Inertial Navigation Systems, or INS. We will explore how these onboard brains use pure mathematics, physics, and microscopic structures to strike targets 1,000 kilometers away without ever using GPS. To understand how we got here, we have to look at the sheer scale of electronic warfare in Ukraine. Entire oblasts are constantly blanketed by GPS spoofing zones, creating massive areas where civilian aviation is warned of navigation failures and military drones are instantly blinded upon crossing the border. When a standard commercial drone enters these zones, its flight controller panics. Without GPS to correct its drift, it either drifts aimlessly with the wind or triggers an automatic return-to-home sequence, flying straight back into the path of waiting air defenses. It is a digital trap. But military-grade, long-range strike drones do not panic. They do not turn back. When they cross into jammed airspace, their onboard systems silently transition to an isolated, unjammable form of navigation. They go dark to the outside world, yet they know exactly where they are going. This silent transition is the key to deep strikes inside Russian territory. By bypassing the need for satellites, these machines have resurrected a method of navigation as old as human exploration, transforming ancient maritime wisdom into a high-speed, mathematical weapon of precision. At the heart of inertial navigation is a concept known as dead reckoning. It is the process of calculating your current position by using a previously determined position and advancing that position based upon your estimated speed, elapsed time, and direction of travel over the journey. Think of it this way. If you close your eyes and take 5 steps forward, turn 90 degrees to your right, and take 5 more steps, you can still draw a mental map of exactly where you are in the room. You did not need a GPS satellite to tell you that your brain calculated your movements. An inertial navigation system does exactly this, but at the speed of sound and with microsecond precision. It requires no signals from the outside world, no radio waves, no light, no sound. It is entirely self-contained, blind, and deaf, making it completely immune to any form of electronic jamming. The math behind dead reckoning is simple in theory, but incredibly demanding in practice. If you know your starting coordinate, your exact velocity vector, and the duration of your flight, you can integrate velocity over time to find your new position. But how does a machine measure its own movement in empty space? To measure movement without external landmarks, an INS relies on the laws of classical physics, specifically Newton's laws of motion. It measures the forces of inertia acting upon internal masses. By tracking these forces, the system can calculate acceleration, velocity, and finally distance. Historically, this required massive, delicate mechanical systems. Early ballistic missiles used heavy, gimbaled platforms with rapidly spinning mechanical gyroscopes to remain stable in space, while accelerometers measured the rocket's thrust. These systems were brilliant, but heavy and expensive. A mechanical INS was a work of art featuring ultra-precise bearings and floating liquid suspensions to minimize friction. Any friction in the gimbals would introduce tiny errors, and in the world of inertial navigation, a tiny error at the start grows into a massive deviation over time. These mechanical monsters guided the first nuclear missiles in the Apollo spacecraft. But they weighed hundreds of pounds, consumed massive amounts of power, and required constant maintenance. They were completely impractical for cheap, expendable, long-range strike drones. To make cheap, long-range drones viable, engineers needed a way to shrink this entire guidance system down. They needed to eliminate the spinning wheels, the heavy gimbals, and the delicate bearings, replacing them with solid-state components that could survive the violent vibrations of a drone flight. This technological leap was made possible by the development of MEMS microelectromechanical systems. By etching microscopic mechanical structures directly into silicon wafers, engineers created a new class of sensors that changed the face of autonomous warfare forever. This brings us to our peak engagement moment, the microscopic world of MEMS. Inside the brain of every Ukrainian long-range drone is a tiny silicon chip. If you zoom in past the plastic casing, you will find a microscopic world of suspended silicon structures vibrating at incredibly high frequencies. At this scale, we find the MEMS gyroscope. Instead of a spinning wheel, it uses microscopic silicon tuning forks. These tiny forks are kept vibrating by an electrostatic charge. When the drone rotates, the Coriolis effect exerts a force on these vibrating forks, causing them to shift laterally. This microscopic lateral shift changes the electrical capacitance between the tuning forks and the surrounding silicon electrodes. By measuring this tiny change in capacitance, often on the scale of femtofarads, the onboard computer calculates the exact rate of rotation in degrees per second. To track movement in 3 dimensions, the drone needs 3 of these microscopic gyroscopes oriented perpendicular to each other. Together, they measure the drone's rotation across all 3 axes: pitch, roll, and yaw. This defines the drone's orientation in the sky. But knowing your orientation is only half the battle. You also need to know how fast you are moving. For this, the chip contains 3 MEMS accelerometers. These sensors measure changes in velocity along the 3 linear axes: forward-backward, left-right, and up-down. Just like the gyroscopes, the accelerometers detect movement by measuring the displacement of a microscopic mass suspended on silicon springs. As the drone accelerates, the mass lags behind due to inertia, changing the capacitance and generating a precise electrical signal. By combining the data from 3 gyroscopes and 3 accelerometers, we get an inertial measurement unit, or IMU. This single tiny chip, costing only a few dollars, continuously outputs a stream of raw acceleration and rotation data hundreds of times every single second. But raw data is not navigation. It is just noise and raw forces. To turn these microscopic movements into a precise flight path, the drone's onboard processor must perform continuous high-speed mathematical integration, translating acceleration into velocity and velocity into position. This process is incredibly demanding. If the drone tilts slightly, the accelerometer will register a portion of gravity as forward acceleration. The system must use gyroscope data to constantly subtract the force of gravity from its calculations, keeping its coordinate frame perfectly aligned with the Earth. This hardware revolution is what allows Ukraine to manufacture long-range strike weapons in small workshops. By utilizing mass-produced commercial MEMS chips, the very same chips found in your smartphone, engineers can build guidance systems that are immune to electronic warfare. But MEMS technology has a dark side, a fundamental physical flaw that keeps aerospace engineers awake at night: cumulative drift. Because an INS calculates position by continuously adding new measurements to old ones, any tiny error in the sensor is added to the total, forever. This is the mathematics of drift. If an accelerometer has a microscopic bias of just 0.01 meters per second squared, an error so small you could never feel it, that error is integrated twice over time. After 1 hour of flight, that tiny bias will cause the drone to miss its target by kilometers. The gyroscope is even more critical. A tiny angular drift of just 0.1 degrees per hour means the drone's understanding of forward slowly rotates. Over a 1,000-kilometer flight, a fraction of a degree of rotational error translates into missing the target entirely, hitting empty fields instead of the objective. This is why cheap MEMS sensors are a double-edged sword. While they are cheap and light, their drift rate is exceptionally high compared to military-grade ring laser gyroscopes. A cheap drone flying purely on MEMS ends would be completely lost after just 30 minutes of blind flight. To combat this, engineers must understand the sources of drift. Temperature fluctuations are the primary enemy. As the drone climbs into the cold night air, the physical properties of the silicon chip change. The tuning forks expand or contract, shifting their resonant frequency and introducing bias. Vibration is another major source of error. The piston engine of a low-cost drone shakes the entire airframe violently. This high-frequency mechanical noise can easily overwhelm the delicate microscopic vibrations of the MEMS sensors, masking the true movement of the drone. Without a way to correct this drift, long-range inertial strikes would be impossible. The drones would simply wander off into the sky, expensive firecrackers that miss their mark. Ukrainian engineers had to find a way to reset the inertial clock mid-flight without relying on GPS. They solved this using advanced mathematical algorithms, specifically the Kalman filter. This algorithm acts as a real-time mathematical referee, constantly comparing the noisy, drifting data from the inertial sensors with other, independent physical clues to find the absolute truth. The Kalman filter knows that the INS is highly accurate in the short term, but drifts over time. By combining it with auxiliary sensors that are noisy in the short term, but stable in the long term, the filter can continuously estimate and subtract the inertial drift, keeping the system accurate. But what are these auxiliary sensors? How do you get a reference point when the sky is completely jammed? This is where the true brilliance of Ukrainian drone engineering comes to light, combining cheap, everyday sensors with sophisticated software to create unjammable eyes. This brings us to Phase 5. Sensor fusion. To stop the drift, engineers do not rely on a single sensor. They combine the INS with an array of simple, passive, and completely unjammable devices. The first of these is a simple, downward-facing optical flow camera. Just like the optical sensor on the bottom of your computer mouse tracks movement across your desk, the drone's optical flow camera tracks the movement of the ground below. By analyzing how fast features like roads, trees, and rivers move across the sensor, the computer calculates ground speed. This ground speed calculation is incredibly valuable. While the accelerometer might drift and think the drone is accelerating, the optical flow camera can look down and say, no, our speed relative to the ground is constant. The Kalman filter uses this to instantly correct the accelerometer's drift. But optical flow has limitations. It requires visible light or infrared illumination, and it can be fooled by low visibility, fog, or flying over featureless water. To supplement this, the drone also utilizes highly sensitive magnetic compasses shielded from the drone's own electrical noise. The magnetic compass provides an absolute heading reference. Even if the gyroscope drifts and loses its orientation, the compass can anchor the system, preventing the heading from wandering. But a compass can be distorted by metal structures on the ground or the drone's own motors. This is why sensor fusion is so powerful. No single sensor is perfect. The INS is highly accurate but drifts. Optical flow is accurate but needs light. The compass is stable but subject to magnetic interference. By fusing them together, the strengths of one sensor cover the weaknesses of the others. This fusion is performed in real time by the flight controller. It is a continuous mathematical dance, calculating probabilities and adjusting weights. If the optical flow sensor suddenly detects nothing but fog, the system automatically shifts more weight to the INS and compass. But even with sensor fusion, a drone flying thousands of kilometers over long periods will eventually accumulate enough drift to miss its target. To achieve pinpoint accuracy, the system needs an absolute unjammable way to verify its position on the globe. It needs to read the map of the Earth itself. This is where the technology transitions from simple navigation to advanced terrain matching. By utilizing the unique contours of the Earth's surface, the drone can find its way across continents with the same precision as a human hiker reading a topographic map. This technology was once reserved for multi-million-dollar cruise missiles like the American Tomahawk. Today, thanks to the exponential growth of computing power, Ukrainian engineers have adapted it to run on cheap, low-power, single-board computers inside wooden and plastic drones. This brings us to Phase 6. Terrain Contour Matching, or TERCOM. This is the ultimate drift-correcting system. Before a drone is launched, engineers load a highly detailed 3D digital elevation map of the entire flight path onto its onboard solid-state memory. During the flight, the drone uses a downward-facing radar or laser altimeter to continuously measure the exact distance to the ground below. By subtracting this distance from its barometric altitude, the drone calculates the absolute elevation of the terrain it is currently flying over. As the drone flies, it collects a series of these elevation measurements, creating a unique profile of the hills and valleys below, like a physical fingerprint of the terrain. The onboard computer then takes this real-time profile and compares it to the preloaded 3D map. The computer slides the measured profile across the digital map until it finds a perfect mathematical match. Once the match is found, the drone knows its exact location down to a few meters. This instantly resets the accumulated INS drift error to 0. Tercom is incredibly effective, but it has one major requirement. The terrain must have unique features. Flying over a perfectly flat, featureless plain or a calm ocean provides no unique contours to match. For these regions, engineers use an even more advanced system, DSMAC. DSMAC, or Digital Scene Matching Area Correlation, uses an optical camera instead of a radar altimeter. It takes high-resolution photos of the ground and uses computer vision algorithms to match visual landmarks like road intersections, bridges, or building shapes to preloaded satellite images. By using artificial intelligence and edge detection algorithms, modern DSMAC systems can match landmarks even if they are covered in snow, wet with rain, or partially destroyed. This gives the drone a level of visual intelligence that is almost impossible to deceive. These terrain matching systems are completely passive. They do not emit strong radio signals that can be tracked by air defenses. They simply look and listen, navigating through the dark like silent predators, completely immune to the electronic chaos raging around them. The combination of INS, sensor fusion, and Tercom creates a layered, redundant navigation suite. If the GPS is jammed, the INS takes over. If the INS drifts, the optical flow stabilizes it. If the drone flies for hours, Tercom resets the drift. It is an elegant, bulletproof engineering solution. This is how Ukrainian drones are able to bypass Moscow's dense air defenses and strike specific buildings with pinpoint accuracy. They are not guided by satellites. They are guided by the very shape of the Earth, navigating through a world where GPS is dead. But the battle for the sky never stops. As air defenses evolve, engineers are already looking to the next frontier of unjammable navigation. This is Phase 7, the future of navigation. And the most exciting development in this field is quantum navigation. Quantum navigation replaces silicon tuning forks with clouds of supercooled atoms. By trapping rubidium or cesium atoms in a magneto-optical trap and cooling them to near absolute zero, scientists can create quantum matter waves that are incredibly sensitive to acceleration and gravity. These quantum sensors, known as atom interferometers, can measure acceleration and rotation with an accuracy that is orders of magnitude greater than the best mechanical or optical gyroscopes. They have virtually zero drift, allowing a drone to fly for days and still hit a target within centimeters. With quantum navigation, the concept of drift disappears entirely. A weapon launched from one side of the globe could travel to the other side in complete silence, without ever receiving a single radio signal, and strike its target with the accuracy of a laser-guided bomb. Another revolutionary future technology is gravity anomaly navigation. Instead of matching terrain height, the drone uses an incredibly sensitive gravity meter to measure the tiny, localized variations in the Earth's gravitational field caused by dense underground rock formations or deep ocean trenches. Because gravity cannot be jammed, blocked, or altered by weather, gravity anomaly navigation is the ultimate unjammable system. It works in complete darkness, through thick clouds, underground, and even deep underwater, providing an absolute positioning reference that is impossible to disrupt. While quantum sensors and gravity meters are currently too large and expensive for small drones, rapid advances in microfabrication are shrinking these devices at an astonishing rate. Within a decade, we may see quantum-grade navigation chips inside everyday consumer electronics. This democratization of high-precision navigation will have profound implications. It will mean that the absolute military monopoly on long-range precision strike capabilities is gone forever, replaced by a world where anyone can build an unjammable cruise missile in their garage. We are witnessing a fundamental shift in the nature of technological power. The centralized infrastructure of space-based navigation is being defeated by decentralized edge-computed physics. The sky is no longer controlled by those who own the satellites, but by those who master the algorithm. This technological shift is not just changing how wars are fought, it is changing the strategic balance of global power. Affordable, unjammable precision is the new equalizer, allowing smaller nations to project power across vast distances with unprecedented efficiency. This brings us to our final phase, the strategic implications. The integration of INS and terrain matching into low-cost drones has effectively democratized long-range strike capabilities. Missions that once required $1 million Tomahawk cruise missile are now being performed by $20,000 drones. This cost asymmetry is devastating for traditional air defense systems. Firing $1 million Patriot missile to intercept a $20,000 drone is economically unsustainable over a long conflict. The defender is slowly bled dry, one cheap target at a time. Furthermore, because these drones do not rely on GPS, they cannot be stopped by electronic warfare. They must be destroyed physically, using kinetic weapons like guns or missiles. This forces the defender to deploy expensive, short-range air defense systems around every single potential target. This stretches air defenses to their breaking point. No nation has enough air defense systems to protect every factory, oil refinery, and military base across a country as large as Russia. By bypassing electronic jamming, INS-guided drones have made geography itself a weapon. The conflict in Ukraine is a living laboratory for the future of warfare. It has proven that the high-tech, space-dependent weapons of the West are incredibly vulnerable in a peer-to-peer conflict. The future belongs to autonomous, self-contained systems that can fight and win in a digital desert. As we look to the future, the lessons learned on the battlefields of Ukraine will shape military doctrine for decades. The reliance on vulnerable satellite networks will be reduced, replaced by a renewed focus on robust onboard sensor suites and localized edge-computed intelligence. The machines are learning to fly blind, and in doing so, they are becoming unstoppable. The silent revolution of inertial navigation has changed the sky forever, proving that sometimes the most advanced way forward is to look inward, relying on the elegant laws of physics. If you want to understand the technology that is actively reshaping our world and the future of global conflict, make sure to subscribe to Weapon Science. We dive deep into the engineering, physics, and strategy behind modern weapons, bringing you the stories that mainstream media misses. Let me know in the comments below, do you think satellite navigation like GPS is obsolete for modern warfare, or will we see a new generation of unjammable satellites? Don't forget to hit the like button and share this video with anyone who loves aerospace engineering. Your support keeps us going. Thank you for watching Weapon Science. Stay curious, stay informed, and I'll see you in the next deep dive. Until then, keep exploring the incredible science that powers our modern world. Ethan Walker signing off.